Hello and welcome to this lesson. We are starting a new unit talking all about rational and irrational numbers. So most of the next bunch of lessons are talking about them, converting one to another, comparing, ordering, lots of various things like that. So this first lesson is entitled Determining if a number is rational or not. Right? Central question, how do I determine if a number is a rational number or an irrational number? Did you know that all numbers in mathematics can be broken down into a few different categories? And there's actually more that I'm showing here, but these are the main ones. From a rational number, which we can see right here in this circle. Let me get him out of the way. So there's a rational number here. Irrational numbers, integers, whole numbers, there's real numbers, there's even something called an imaginary number, which would be a little bubble on the outside here. There's a whole bunch of different types of numbers. We are focused on the difference between a rational number and an irrational number. So let's figure out what the heck these things are. A rational number is any number that can be written as a fraction. This includes those integers, repeating decimals, and terminating decimals. So an integer, in case you don't know, is a number like 5 or -3. It's a whole number, but it's allowed to be positive or negative. A repeating decimal would be something like 1.83 repeated, or -6.193 repeated, where there's a repeating pattern that repeats itself forever infinitely. And then finally, a terminating decimal would be a decimal that stops. Terminating means stops. So 3.6 is a terminating decimal. -1.932 is a terminating decimal. As long as it stops, it terminates. So all of these numbers can be written as fractions, and we're going to talk about that throughout the next bunch of lessons. Irrational numbers, on the other hand, is any number that cannot be written as a fraction. It cannot be done. It is impossible to write it as a fraction. So let's figure out how we can tell them apart. So, a rational number. For each of the number below, if the given number, for each example, determine if the given number is rational or irrational. Okay, so our goal, is it rational or not? So looking at example A here, I want to know, is this rational? Well, is that an integer? No, it's not a whole number. It has a decimal. Is it a repeating decimal? Yes, that's just 0.12 repeated. 1, 2, 1, 2, 1, 2, 1, 2. That is rational. And we don't need to know it for this lesson, but that as a fraction is 12/99. We will talk about that in future lessons. And that fraction could be simplified if we did 12 fraction 99 it does not kind of like that. 12 fraction 99. It would just been easier if I just did this by hand. Divide top and bottom by 3 and get 4 out of 33. See, sometimes the calculator is not your best friend. Sometimes your brain is your best friend. Letter B. Is that a rational number? Well, yes, I can write that as a fraction. That's just -9/1. That's what it means to be a rational number. Can you write it as a fraction? Yes. And we also saw in the definition that integers, which -9 is an integer, integers are rational numbers. All right, another one for me, 3/4. Is that a rational number? Can you write that as a fraction? Yes, it's already a fraction. It's already 3/4. So this is rational. Letter D, I want you to try that one. What do you think? Do you think 0 is a rational number? The answer is yeah, it is actually. Because I can write the number 0 as a fraction. 0 over 1. If I were to divide that on my calculator, 0 divided by 1 is 0. That's okay. It's the same value. I can put 0 fraction 1, and that's okay. So yes, 0 is a rational number. It is also technically, you could write it as a terminating decimal, just 0.0. So lots of reasons it's rational. Letter E, I want you to think about it. I want you to try it. Can you write that thing as a fraction, and maybe even try to write it as a fraction? Hint, hint. Right now it's not a fraction, it's a mixed number. Is it possible to write that as a fraction? Pause the video, try it. When you're ready to continue, hit play, and we'll do it together. So the answer is yes, he is rational. As a fraction, maybe you remember how to do this. You multiply the denominator times by the whole number, and then you add the numerator, and this would give you 4 thirds. That's what it would be as a fraction. Excuse me. So yes, it is a rational number because it can be written as a fraction. As a decimal, just to show you, 4 thirds is a repeating decimal. So again, repeating decimals are rational. Another reason why this is rational. The number pi, which I have there, 3.1415925. It's actually 5389796 something or other. Is that a rational number? No, it's actually not. This is irrational because it is a decimal that does not stop. The number pi goes on forever and ever and ever and ever. It never stops. It never repeats. And it, as I say, it does not have a repeating pattern. If I go to a website here, I probably have a copy of it. Nope. All right. So, no, not Desmos. I want Wolfram Alpha. This is a pretty cool little website that you can type in kind of mathematical science thingies in it, and it will calculate for you. So I'm going to type in pi and say go. And if you look here, there's the decimal approximation, 3.141592653589793 and it goes on. And I can add, well, I can't click with my mouse, I gotta use the iPad. More digits, and more digits, and more digits. There's no repeating pattern in any of these numbers. Okay, this goes on forever. Okay, so pi is irrational. It cannot be turned into a fraction. There is no repeating pattern. It's irrational. And a lot of the numbers that have pi attached to them, like 3 pi, that will also be irrational because it's that same big, huge, long number, just 3 times bigger. Imagine you multiplied every single one of those digits by 3. It's just 3 times bigger, but it's still going to be irrational. Letter G. So you may not have seen an expression like this before. This says 4 square roots of 30. Now that means 4 times the square root of 30. Is this irrational? Well, a way you could figure this out is you can use your calculator. 4 square root is this number, the symbol right above the 7 here, if you're using the same calculator as me. 4 square root of 30 equals 21.908923. Now, as far as we can see, there is no repeating pattern. So we could relatively say that this is going to be irrational. And there's a few reasons for that. One is, if you take the square root of just 30, whenever you take the square root of a number, if you don't get a nice, pretty, perfect answer, like 5 or like 2, it's irrational. Now let's compare this. If I take the square root of 36, watch what I get. I got a nice, pretty, perfect answer. 6, whole number answer. If I take the square root of anything that is not a perfect square, say 29, that's irrational. Square root of 28 is irrational. Square root of 27 is irrational. I swear, I'm almost done. Square root of 26 is irrational. Square root of 25 is a rational number. All of those other digits on our calculator, these were all irrational numbers. And I know that because if you take the square root of a number and you don't get a nice, pretty, perfect answer, it's going to be irrational 100% of the time. So I know that square root of 30 is irrational. And if I take that and times by 4, it's going to be 4 times bigger, but it's still irrational. All right, one for me, one for you. Go ahead and try negative 49 over 7. Is that a rational number? And yes, it is. Because, well, first off, it's already a fraction. 49 over 7, that's a fraction. That fraction could be simplified down to just negative 7, which is an integer, which is rational. You could, and so for, lots of reasons, this is a rational number. Example 2. Our second skill is now instead of just given a simple number and being able to figure out if it's rational or not, we're going to be given an expression. So we are going to evaluate the expressions. Evaluate the following expression. That means do the math, simplify, figure out what that number is as a decimal or as a fraction. Then determine if the expressions have rational or irrational solutions. So basically, I want to figure out, is this number here a rational or irrational number? All right. Now, a lot of these, you can go straight into the calculator. Now, we're going to do that with a lot of them, but we're also going to talk about them. So the first one here, 1 fraction 2, 1/2, get out of your fraction, times 5 times 9 is going to give us 22.5. Told you so. 22.5. That is rational. And I know that because 22.5 is the same thing as 22.5, and that is a terminating decimal. My 22.5 I could also write as a fraction. 22.5 as a fraction would be 45 over 2. Letter B, 9 pi. Well, we saw in our discussion that when I went into Wolfram Alpha that pi itself is an irrational number. 3.141592653588979, blah, 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 blah. It goes on forever. So if pi is an irrational number, and I take it times by 9, excuse me, imagine I have a number 3.141592653588979. I ran out of space on my iPad. And I took that, and you had to multiply by hand, and you multiply by 9. You would have to take every single one of these digits multiplied by 9. But remember, pi doesn't stop right here. Pi goes on forever and ever and ever and ever and ever. So the answer you get is still going to be forever long. There's no way those decimals are going to get chopped off. There's no way it's going to be now a repeating decimal or a terminating decimal. So it's still going to be an irrational number. If you take an irrational number times by something, it's still going to be irrational. Okay, here are two for you to try. Go ahead and pause the video. Try these two on your own. Feel free to use your calculator if you need to. And when you're ready to go through them together, hit play, and we'll do just that. All right, letter C. So the way I would do this is I would probably do more by hand than by calculator. If I'm going to simplify this, I would do the math across the top here first. I would do 6 minus 3 is 3. I would do 8 plus 9 is 17. And then, let's see. If I take 3 divided by 17, I get 0.176470. That looks like a big ugly mess, doesn't it? And so now I'm a little confused, because the rule is if you can write it as a fraction, it's a rational number. Here it is. That's a fraction. That's probably a rational number. But its decimal is a big ugly mess. And we've seen pretty much before, any decimal that we don't see a repeating pattern and doesn't stop has been irrational. Well, this number is a rational number. Because again, the fact that you can write it as a decimal proves this is rational. If I go back into Wolfram Alpha, and I'm going to type in 3 divided by 17. Let's see what Wolfram Alpha says. Okay, so it's verifying. So I inputted 3/17. It says it's irreducible, which means I cannot simplify that fraction. It gives me a decimal approximation. Now, if you look at this, you can actually see there's a pattern. I can't do it on my, okay. Oh man, that's a picture, I think. I'll see if I could like highlight text. So from here up to right here is the decimal. 1764705, blah, 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 the whole way up to right here. And then repeat. See these double ones? 1764705, 1764705, 1764. So this is a repeating pattern. We just can't see it on our calculator. But we knew it was a rational number because it already started as a fraction. Any number as a fraction is rational. That is the definition of what a rational number is. Letter B, or D. Let's see. If we calculate just even the square root of 8, guaranteed irrational number. If I take that and I times by 4, it is now a 4 times bigger irrational number. If I take that new irrational number and I add 5 to it, imagine, plus 5. I know I didn't times by 4 here. We'll do it right. Square root of 8, boom, it's irrational. Times by 4, boom, still irrational. Add 5, well, it's still irrational. The decimals aren't going away. I just made the whole number bigger. This is irrational. All because of that piece, because he started irrational and there's nothing in this problem to get rid of that irrational number. There are some times where you can, and I think we'll see one of those soon. So letter E, we have square root of 100 over 9. Oh, let's just do that. I could potentially do that in my head, but we also have a calculator. Let's see what it says. That's simplified to a nice, pretty answer. 3 1/3, which means this is rational. You'll see and hear me a lot of times. A phrase that I use is rational numbers are typically nice, pretty decimals. Where irrational numbers are usually big, ugly decimals. And I know my handwriting's a little sloppy there, but this, when I simplified this, we got 3 1/3, which is a decimal. If I hit the little decimal button, is 3.3 repeated. That's a nice, pretty decimal. That's short. It stops. There's nothing terribly ugly about it. Whereas letter F, if I type this in, so 4 fraction 3, I can get out of the fraction. I can hit pi. I can even do the parenthesis thing. There you go. I typed in exactly what it says there. I hit enter. Now, the calculator is weird. There's a mode you can change in your calculator so that it will get rid of the pi thing, auto simplifying stuff, but whatever. You also have this little convert button, and that's what I would do. Now, calculator doesn't show too many digits there, but that is irrational. And we can logic through that because pi is irrational. If I multiply that by 4/3, it's still irrational. It's just 1.5 times bigger. Or 1.3 repeated times bigger. If I then take that irrational number and I times it by 36, which is what 6 squared is 36, it's now going to be just 36 times bigger, this infinitely long, huge, massive, ugly number that doesn't have a repeating pattern. It is still irrational. It will be a big, huge, ugly decimal that never stops and does not have a repeating pattern. Okay, letters G and H. Go ahead and pause the video. Try these two on your own. When you're ready to continue, hit play, and we will go through it together. Now, if you're looking at both of these and going, wow, those are both rational numbers because they have decimals. I'm sorry, because they're fractions. Can you look at this and go, hey, look, it's a fraction, and hey, look, it's a fraction. Not quite. There is a definition of a fraction. The actual honest definition of a fraction or of a rational number is where you have it's a whole number, it's an integer over another integer. So like 3/5 is allowed. These are both integers. They're whole numbers, they're not fractions or decimals, and they're allowed to be positive or negative. I could have that, which is okay. I could have that, which is okay. It's still rational, but you're not allowed to have something like that. That is technically not a fraction. That is technically not a rational number yet. Now, I could simplify it and do other things, but right now it's not considered a rational number because this number up top is not a rational number. I could do fancy things like rewriting this 32/50. These now have the same value. And that is a rational number because now there's no decimals in it. Okay, now, big long conversation. Why are we doing this? Well, because this number right here, letter H, I know we skipped to G for now. We'll come back. This problem here, letter H, is like that same example. Like, this technically is not a fraction yet. It's not a rational number because I have decimals inside my fraction, and that's not allowed. But with a little bit of trickery, we could go vump, 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 vump. As long as we move our decimal the same number of places, top and bottom, we're good. That's not a 5. 2587 over 1590. That is a fraction. And that means this is a rational number. I'm not sure if our calculator can do that. 25.87 fraction. Okay, it puts the negative sign out front. That's okay. 15.9. And I'm going to get out of here. I'm going to hit the little switcheroo button. Equals. Okay, that's a decimal. Nope, it can't change it to a fraction for us. Let me go back up. Can I? Okay, so here's what it is as a decimal. This negative 1.627. Now, if I do this, negative 2587 divided by 1590. I'm going to type this in and hit equals. Do you see how it's the exact same number? So as a fraction versus this is when I just try to have the calculator change it to a fraction. Yeah, the calculator doesn't like it. Probably because this the fraction here probably does repeat. It's just going to take a very long time. It might take 15 digits or 16 digits for it to repeat, as opposed to some of the other ones that are pretty tiny. All right, we skipped letter G. Let's go back to it. So letter G, you might have found that this number is actually rational. I deleted it for a second there, but I need it back. Not irrational, which is confusing for some students because they look at this and they go, but wait a second, Mr. Henry, there's a pi right here. And pi means that this piece up top is irrational. This is irrational, and there's an irrational number, and that means that this problem is going to be irrational. Sort of. Check this out. And it's okay if you got confused on this. That's kind of why we're going it together. So the top doesn't simplify. That's just 6 pi. The bottom does simplify a little bit. 4 times 2 is 8. So this becomes 8 pi. These pi's can cancel out. It's considered a common factor of the top and bottom. Just like if you had, that's 15 and that's 12. Whoa. 12. 15 over 12. You could divide the top and bottom by 3 because they're a common factor, and those 3's cancel out and you get the fraction 5/4. Well, these pi's are a common factor, and I can cancel them out. And we're going to get 6/8, which is 3/4 as a fraction, or 0.75 as a decimal. This is rational. If you are careful in how you put this into the calculator. 4 parenthesis 2 pi, close parenthesis, over, enter. Look at that. So I typed in the problem into the calculator. It says 6/8. The little arrow means we can simplify. So simp equals 3/4. It tells me that it divided by 2. So the calculator knew that the pi's canceled out. The calculator gave us a nice, pretty answer. Maybe you weren't sure why, but that's why, because those pi's actually can cancel. So you got to caution yourself that every time you see a pi doesn't always mean irrational. There's always going to be tricks. There's always going to be exceptions to the rule, or times where it doesn't quite fit the pattern. And that's where your brain comes in. All right, we're on the problem solving already. Here it says Sam has the number 13/19, which when written as a decimal is 0.68421053. Sam does not know if this number is rational or irrational. How would you explain to Sam if his number is rational or irrational? So this problem actually is very similar to a problem we've done once or twice already, where I have a number that this looks like it's a rational number. I mean, it's a fraction, right? So the rule is anything you write as a fraction is rational. So 13/19 looks rational. But that decimal piece is a big ugly decimal that doesn't appear to stop. I mean 13 divided by 19. There. So this calculator shows actually one more digit. The 6 would round this 2 up to a 3, which is why it says a 3 here. But the decimal looks irrational. If I go into Wolfram Alpha and I type in, what was it, 13/19? 13 divided by 19, go. And it says it's an input. It cannot be simplified. Here is the decimal expansion, and I'm looking right here is where the pattern repeats. So 68421, 68421, 684. So it takes a while. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 digits it takes before it repeats, but it is a repeating pattern. Well, there it is. It's a repeating decimal. A period of 18 means it was 18 digits before it repeated. So it is a rational number. Because, well, we know that it started as a fraction, which guarantees 100% that this is a rational number. So that's what we need to tell our friend Sam. Hey, Sam, because this number started as a fraction, I don't care what it looks like as a decimal. Because it started as a fraction, this number is rational. The definition of a rational number is any number that can be written as a fraction. Letter B. A soup can is made from a rectangular piece of aluminum that is wrapped into a cylinder. If the soup can has a diameter of 3.5 inches, determine if the circumference of the soup can would be a rational or irrational number. Use the formula for the circumference of a circle, c equals pi d, where c is the circumference and d is the diameter of the circle. So I'm a fan of drawing pictures, so it talks about having a rectangular piece of aluminum that's wrapped into a cylinder. So if you could imagine a soup can, we have this big rectangle, and then the machine takes this and kind of forms it into that shape. It kind of wraps it up. The soup can has a diameter of 3.5 inches. Okay, so let's see. Here's my soup can. I'm labeling stuff. That's my picture. And I'll change color. This diameter is 3.5 inches. Now, diameter, in case you don't remember, is the whole way across the circle, going through the center. You might be confusing that with a radius, which only goes from the center to the outside. A diameter goes from outside to outside through the center. Okay, soup can has a diameter of 3.5 inches. Check. Determine if the circumference of the soup can would be rational or irrational. And they give me a formula. I don't actually need too much more space, and this little rectangle thing didn't actually help me out any. So they give me a formula, c equals pi d. I'm going to plug in what I know. I do not know the circumference. That's actually what they're asking us to find. I know pi is the number 3.14, and I know the diameter is 3.5, because we label it right here. Now, the question is the circumference a rational number or an irrational number? So I know how students get both answers. You could potentially get an answer of, let's see, pi. Pi is 3.14 times 3.5, and you get 10.99, which looks rational. Or, I'll be a fat cheater. Copy, paste. Or, you type in your calculator, pi times 3.5. So instead of putting in 3.14, I just put the pi button, and it gives me 10.99557,429, which looks to be irrational. So how do we know which one it is? Well, it's easy. It's the one that's actual 100% pi, which is the one on the right. The one on the left, when you took this and you made this a 3.14, you rounded pi. You chopped off almost all of its digits. Remember, pi goes on forever. You chopped off a bunch of its digits and you've rounded your answer. You've changed the actual answer to the problem. Most of the time, that's okay. If you're asked to find the circumference of a circle, a lot of times we do round. We don't need all of those digits of pi. But as far as determining if the number is a rational number or an irrational number, you kind of do need all of those digits. So this one is wrong because we rounded and we chopped off all of those decimals. This one, the calculator holds all those decimals and we get a much more accurate answer. This is the correct answer. The actual circumference of that circle will be an irrational number. Letter C. The square tank has an area. How about A a square tank instead of the square tank. A square tank has an area of 45 feet squared. The length of each side of this square would be square root of 45. Okay, I'm going to draw that picture. So a square has an area of, why was I even saying tank? I don't know. A square has an area of 45 feet squared. All right, so here's my square. It has an area of 45 feet squared. The length of each side of that square would be square root of 45. That's how big that side is. Square root of 45, square root of 45. Which is true. Is the length of each side of the square a rational or irrational number? Now, I don't know if you know your square roots off the top of your head, but I don't exactly know what square root of 45 is, because 45 is not a perfect square. I know it's not going to give me a nice, pretty, perfect answer. It's going to be irrational. Because square root of 45 is like 6.708203932 ... It goes on forever. It doesn't stop. It does not have a repeating pattern. It is irrational. Letter D. In a fish tank, there are 13 goldfish and 20 fish altogether. Is the ratio of goldfish to all fish a rational or irrational number? And how can you tell? So this is a problem I'd like you to try. Pause the video, try it. Do you believe that the ratio of goldfish to all fish is rational or irrational? And why? When you're ready to continue, hit play, and we'll go through it together. All right, so when I write this ratio is a fraction, or a fraction is one way to write it. The ratio of goldfish to all fish would be 13 to 20. Is this a rational or irrational number? Well, it is definitely a rational number. Because, as you can see, it is already a fraction. That fraction does not simplify, but it is already a fraction. It is a rational number. And then how can you tell? Well, it's a fraction. It's a fraction. If I take 13 divided by 20, I'm actually going to get a terminating decimal too. That's equal to 0.65, which is a terminating decimal. That's a rational number. Last skill for this lesson is doing a little bit of, well, this one says, which of the following lists are made of entirely rational numbers? So I've got 4 different sets of numbers here. Which of these sets, A, B, C, or D, only has rational numbers in it? So actually what I'm doing is when I'm doing this in my brain, I'm looking for which ones are irrational. So I'm going to take my highlighter out. I'm not going to use yellow. Let's use pink here. So square root of 40 stands out in my head. I am not positive if that is a rational number or not. If I square root 40, I find out that he is irrational. It did not give me a nice, pretty, perfect answer. Like if I did square root of 49, that would have been a rational number. But square root of 40 is irrational because I get a big, ugly decimal. So it is not letter A because that is not only rational numbers. Letter B. I'm going to check that square root. Square root of 81. Oh, that is rational. Whoa, wrong pen. That's rational. 0 is rational. We talked about that earlier. 9 and 3 over 37. That's rational because that can be written as a fraction. Negative 9.87654. Well, it's not stopping. ... means it's not stopping. And as far as having a repeating pattern, that would be a pattern that repeats itself forever. We don't see one. So my only conclusion is that this piece here is irrational. So it's not letter B. Letter C, things that stick out of my brain, at least things that check. I've got a 5 pi and I've got a this thing. Now, we've done quite a bit of talks on stuff like this. This is going to be irrational because, again, pi is irrational. If I multiply that by 5, it's just 5 times bigger, irrational. Which means it pretty much has to be letter D, or none of them are. So, do any of those stick out at your head that's being a little weird? Maybe the square root, if you're not good with perfect squares. 15/19, he's already a fraction, guaranteed rational. This is a repeating decimal, guaranteed rational. This is a mixed number with fractions, which means I can turn this into a fraction. That would be 32 over 12, negative 32 over 12, which is rational. So let's check this. 4 square root of 36 equals 24, which is rational, which means letter D is the correct answer. That is the one that only had rational numbers in it. All right, summary. What is the difference between a rational number and an irrational number? Put down your thoughts, pause the video, think about it. When you're ready to continue and go through it together, hit play, and we'll do just that. All right, so the difference between them is a rational number can be turned into a fraction. Rational numbers are fractions. Rational numbers are usually nice, pretty decimals. Whereas irrational numbers, you cannot put them as fractions. And as decimals, they are big, ugly decimals. They don't stop, and they don't have a repeating pattern. Oh, I don't have space for the word decimals. We can fix it. Big, ugly decimals. Okay. These have terminating decimals. Oh man, that's terminating. Try it again. Terminating decimals and repeating decimals. Versus irrational numbers, they are not terminating or repeating. So I'm going to cheat. Copy, paste, not terminating, and not repeating. Okay, so quick little review of the whole lesson. I'm going to scroll back to the very tippy tops. So things that we learned. We learned the difference between a rational and irrational. We looked at the definitions, and then every single example after that was basically just reinforcing that definition. We learned that rational numbers can be repeating decimals like letter A, or integers like letter B. We learned that rational numbers are fractions like letter C, and whole numbers like letter D. We learned that rational numbers can be as mixed numbers because mixed numbers can be changed into a fraction like letter E. We learned irrational numbers are numbers that do not stop and do not have a repeating pattern. Pi is a very, very common irrational number. So is the square root of lots of numbers. In fact, the square root of most numbers is irrational. As in, square root of 30 was irrational. We learned if you take an irrational number and you multiply it by something, your result is just going to be a bigger irrational number, but it's still irrational. We looked at our second skill was simplifying expressions, and we used our calculator for most of these, and we simplified expressions and determined if our solutions were rational or not. Going on. We learned that fractions the definition of a fraction has to have only whole numbers, top and bottom. You're not allowed to have decimals inside of a fraction. Maybe you didn't know that. And then we just did a little bit of reinforcing with our applications in the bottom, these problem-solving ones. We learned that when you are calculating pi and use the number 3.14, it is an estimation of pi, not the whole actual thing of pi. And so if you're looking at if it's a rational or irrational number, you'd want to use real pi, not rounded pi. And that's been about it. So thank you for watching this lesson on rational and irrational numbers. Toodles.